with the basic rule of counting and then the generalized rule of counting, we're ready to talk about permutations. Okay, so permutations, we're going to start with the definition, but then we're going to use an example to introduce the definition. How many different arrangements of the letters A, B, C? Okay, so arrangements. Okay, and we have 3 different letters that we're making arrangements with. Okay, so well, you can imagine that you can do ABC, right? You can do ACB, right? You can do BAC, BCA. So if you listed out all of the possible cases, if you were to do it, well, that's one way, right? But the other one, as we are trying to use a more mathematical approach here, is that we can think about the 3 places that we're trying to fill, okay, just like the license plates that we're doing earlier, that the first place, well, you have 3 letters to choose from, so there are 3 different ways to do it, right? 3 outcomes. The second one, once you have chosen the first one, well, you only have 2 remaining, right? And the last one, only 1 remaining. So you multiply them. This is, again, the generalized rule of counting, which is, well, 6, okay? So not surprising, right? The results, and this is what we mean by arrangement, and then the different what we mean by different arrangements. So from the arrangement, what we're talking about, let's define permutation. Each of these arrangements is a permutation. Okay, you can think about it as an arrangement, and then in particular, we want to highlight that the order matters. Okay, because ABC is different from BCA. Okay, so it's important to keep in mind that the order matters, and then each arrangement is what we define by a permutation. And more formally, if you have n different objects, like what we're having over here, you have A, B, C, they're all distinct from each other. You have 3 of them, right? So if you have a number of n distinct or different objects, and then you're interested in a number of permutations of the n different objects, meaning that we're wondering the number of arrangements, then a quick, more straightforward expression is what we call the factorial. Okay, some of you probably have seen this definition before, and factorial, well, n factorial is defined to be n times n minus 1 times n minus 2, da da da, and then multiply until 1. Okay, and then while putting into this context, we know that, well, if we are interested in the number of permutations of 3 different letters, then it's going to be 3 factorial. You see that part of the answer is written in this way. And it's, well, if you express it out using the definition, it's going to be 3 times 2 times 1, which is 3 factorial, which is 6. Okay, so this is the most straightforward permutation definition or permutation example here, that when you have n different objects, then directly you do n factorial to get the number of permutations. However, sometimes, right, you might have some objects are the same, and while others are still different from each other. So we're introducing the second permutation definition, or I should say a second permutation expression, okay? An important scenario is permutation of R groups of n objects. The example that we're going to start with is the number of permutations of the letters in the word Facebook, okay? So if we follow what we did before, there are n, well, n factorial, right? The number of permutations if all of the objects are different. However, if we count, okay, there are 8 different letters in Facebook. Okay, so n equals to 8. However, you notice there are 2 O's. They're not distinct anymore. Okay, so immediately you might think that, okay, I might not be able to use what we know already, n factorial, like a factorial directly. So, well, if we look at that, B will be wrong, right? But how can we figure out the number of permutations in this case? Okay, so a factorial gives us the number of permutations if they're all distinct from each other, right? And then we have a duplicate of 2 O's here, meaning that if I spell Facebook like this, or if I spell Facebook again, just switch the 2 order, like the order of the 2 O's, well, it's exactly the same word, right? So intuitively, we'll see that, well, we have to like cancel out that kind of effect when you have duplicated letters, or I should say generically similar objects. So the answer is, we will see that is a factorial divided by 2, okay? But more importantly, let's think about the generic result of this permutation of R groups of n objects. So here, well, like what we were saying, the O's, because they are similar, they are like, unless we add this subscript. So we add this subscript just to show that, well, when you spell it out, it's the same. So the results for this is a factorial divided by 2. Okay, yeah. So in this general results, let's try to focus on R groups of n objects. Okay, so you still have n objects, but not all of them are the same. Okay, and then in particular, you have 2, in this case, 2 O's, and the order of them doesn't matter anymore. So if you want to get a generic result in this case, like what we're showing here, is to get the number of permutations R groups of n objects, is that first of all, you compute the number of permutations if all different, which is 8 factorial, n factorial, like what we know before. But then because the two, like the order of the 2 O's does not matter, no matter where they are actually. So the permutation among the 2 O's, we have to cancel out that effect. And the way to do it is really just dividing, right, the number of permutations among the 2 O's, which we know is 2 factorial. Okay, so in that case, we're canceling out that effect. So we have 8 factorial that we start with, and then we divide by 2 factorial. So if this sounds overall straightforward, let's look at the general result here. If you have n objects, notice that here we no longer say that n distinct or different objects, okay? Because we know that in this case, some of them are alike. Generically, we say that n1 of them are alike, n2 of them are alike, and nr of them are alike. Then the number of permutations, once you're considering n objects and then r different groups here, it's going to be n factorial divided by the product of all of the ni factorial that you are able to consider. So what we have seen before is really a special case, right, of this general result. And this is, again, going up to R groups. So our example, Facebook, we have 8 letters in total, right? And then think about the groups here. Okay, so how many groups we have over here? Each group will be a distinct letter, right? So we actually have 7 groups. F represent one group itself, and then actually N1 in that case is 1 because you only have 1. Okay, same goes for A, goes for C, goes for E, goes for B, and goes for K. They all represent one group with a single letter there. O is the special group here because it has 2 objects. So all of the other ones will be 1 factorial, and then you will have 1, 2 factorial over here. And then we know that 1 factorial is 1, so they all canceled out. So eventually we get what we had before, 8 factorial divided by 2 factorial. Okay, but really this result is more general. Like I said, we're talking about n objects and then r different groups, and we're thinking about the permutation of them. Lastly, let's consider the third scenario when we're talking about permutation is selecting R items of n objects. Okay, so the question, the example that we're going to start with is how many permutations of 2 numbers among 1 through 6? Okay, so, well, we're choosing 2 values, right? 2 numbers out of the 6 different numbers. So again, this is n distinct object, as you can see over here. And then we choose 2, and then we care about their order because it's a permutation. So, well, immediately we know that when we did before, right? The first, so we have 2 places to fill. We have 6 choices for the first, 5 choices for the second. So you multiply them. This is actually the basic rule of counting. You get 30. So the answer will be 30. But let's look at it in a more combinatorial way, and what we're talking about, the factorial results. Okay, so other than 30, when we directly do it, another way to write this is 6 factorial divided by 4 factorial. Okay, it might look a little bit like surprising, like why do we care about the factorial? Why don't we just do 6 times 5? 6 times 5 is correct, as we have seen before. But then another way to think about it is that when you have 6, well, I guess in this case, 6 distinct objects, and then you're choosing 2 of them to form your permutation, it's really like I first of all permute all of them, okay, and they're all distinct, so we know that 6 factorial, okay. And now the question is, well, we pick the 2 of them, so we have the remaining 4. So it's almost like I have 6 factorial different ways of permuting the 6, but the 6 objects, distinct objects, but I really only care the first 2. Okay, so when I do that, it's like the remaining 6 minus 2, their ordering doesn't matter to me anymore. And this is like the canceling effect that we have seen before. So it's really like we're canceling out the ordering of the remaining 4 as we don't care about them. So you can get the ratio 6 factorial over 4 factorial to get the number of permutations. Okay, so more generically, let's look at the results. If I have n items, okay, distinct in this case, and I want to select R of them, the number of permutations, well, we know that we can count one by one up until the last choice is being made, but we can also express it of n factorial divided by n minus r factorial, just like what we have seen over here. Okay, so we first of all, in the numerator, we have the number of ways to permute n distinct objects. And then because we're only choosing r out of them, so we don't care about the remaining n minus r, which meaning that we have to cancel out the ordering of those ones. So we do the division, and the division, the denominator is n minus r factorial, just like what we have seen in the example. Okay, so this is the third and last permutation scenario that we talked about. Okay, I would just leave an open-ended question. What if the order doesn't matter? Okay, what if, well, in handshake scenario, I take a handshake with you, is this, well, it's the same as you take a handshake with me, so the order doesn't matter anymore in this case, so how can we deal with that? So this is an open-ended question, and we will try to answer it in later lectures. So to recap, we talked about the basic rule of counting, okay? And then for permutations, we talked about 3 different versions of permutations. The first one is most straightforward, most basic. The number of permutations of n distinct objects would be directly n factorial, okay? However, if you have n objects, but they're not distinct from each other, not necessarily, okay? And you actually can observe r different groups, with n1 to be the number of objects in the first group, n2, etc., etc. Then the number of permutations of this n objects will have to cancel out, right, the permutation of the alike objects within each group. So you have n factorial divided by the product of all of the n1, n2 until nr factorial. Lastly, if you're curious about the number of permutations of selecting r items out of n objects, that is also some canceling effect, right? Because you can have n factorial permutation that you get started with, but then you have to cancel out that I'm only selecting r of them. I don't really care about the remaining n minus r. So we divide the n minus r factorial in the denominator. Okay, so pay attention to the different scenarios of permutations, and then when working with exercises, make sure that you know that particular context, what kind of permutation we're talking about, and then you're able to apply the correct tool for you. But also very importantly, try to understand the distinctions among the 3 different permutation scenarios, and then understand why they work in this way.